In this video, we are going to discuss question 9.44 and 9.45. Let's begin with 9.44. The question says, a discus thrower with an arm length of 1.2 meter starts from rest and begins to rotate counterclockwise with an angular acceleration of 2.5 radian per second squared. We need to solve question A till F. And before we do that, let us first write down what we have been given. We have the arm length of discus thrower, which is 1.2 meter. And if you look at the sketch here, the arm length can be taken as the distance from the axis of rotation, which I can write as R, 1.2 meter. And since the discus thrower starts from rest, at rest means here my angular velocity, the initial angular velocity omega I, will be 0. Then it has an angular acceleration of 2.5 radian per second square, alpha, which is 2.5 radian per second square. In part A of the question, we need to find how long does it takes the discus thrower speed to get to 4.7 radian per second. So I will write my final angular speed omega f to be 4.7 radian per second. So let us start with part A of the question. We need to find how long does it take to reach this speed. How long means we need to find the time t. Now we know that angular acceleration alpha and angular velocity are related by the expression alpha equals omega final minus omega initial over the time t. And we can find t by multiplying with t on both sides and dividing by alpha. So we are basically going to cross multiply and switch these two quantities. I will take t up and bring alpha down. So we write t equals omega final minus omega initial over alpha. And when we substitute, omega final is 4.7, initial is 0, alpha is 2.5. That gives you the value of t as 1.88 seconds. In part B, they're asking us how many revolutions does the thrower make to reach a speed of 4.7 radian per second. So we need to find the number of revolution n. Before we find the number of revolution, we need to find the angular displacement delta theta of the discus. So since we have omega initial, alpha, and time t, I will use the third equation of motion to calculate delta theta, which is delta theta equals omega I t plus half alpha t squared. This is similar to the third equation of motion we do for linear values, where we write delta x as vit plus half at squared. Here x, v, and a I have replaced with theta, omega, and alpha. So let's calculate that. Delta theta will be equal to omega initial is 0. So when you multiply that with t, the whole term becomes 0 plus half. Alpha is 2.5. T we just calculated as 1.88 squared. And when you solve it, you get delta theta as 4.418 radian. Now, when an object completes one revolution, in one revolution, it covers an angle theta equals 2 pi radian. So how many revolution will it make if d theta is 4.418 radian? You can calculate this number of revolution by dividing your delta theta with 2 pi. Because if one revolution gives you 2 pi radian, 4.418 will give you number of revolution equals to this number divided by 2 pi. So let's calculate that. Delta theta is 4.418 divide by 2 pi, and that gives you the number of revolution as 0.703. So anytime question asks you to find number of revolution, you can directly use this rule delta theta over 2 pi. But to use this rule, you need to calculate delta theta, which you can get from any one of the equations of motions. Part C of the question is asking you, what is the linear speed of the discus at 4.7 radian per second? So I need to find the linear speed v. The linear speed v is related to angular velocity as v equals r times omega. And since I need to find this speed at 4.7 radian per second, which is my final angular speed, I will write this as r times omega final. So we can multiply r 1.2 times omega, which is 4.7, and you get the linear speed of the discus as 5.64 meter per second. Then in part D, the question is asking you, what is the linear acceleration of the discus thrower at this point? Linear acceleration A, we can calculate using the rule A equals r times alpha, which is equal to 1.2 times alpha is 2.5 radian per second square. And that gives me the linear acceleration as 3 meter per second squared. Part E of the question is asking us, what is the magnitude of centripetal acceleration of the discus thrown? Now, centripetal acceleration is given by the expression AC equals v squared over r. Linear speed v we have already calculated, which is 5.64. So I will write 5.64 squared divided by r, which is 1.2. And when you solve this, you get your centripetal acceleration as 26.51 meter per second squared. This centripetal acceleration you can calculate using any one of the rule given to you, either v squared over r or r omega square or v times omega. In this particular question, we have all of these values and you can use any one of the equation to calculate centripetal acceleration. Now the last part of the question is asking us, what is the magnitude of the discus total acceleration? The total acceleration A is the resultant of centripetal acceleration and your linear acceleration AT. So we can calculate A as square root AC squared plus AT squared. So my linear acceleration is AT, which we have calculated in part D, and centripetal acceleration is AC, which we got in part E. I will substitute their values here. AC is 26.51 square of this plus 3 squared. And when you solve this, you get your total acceleration as 26.68 meter per second squared. Now let's solve question 9.45. In a department store toy display, a small disc 1 of radius 0.1 meter is driven by a motor and turns a larger disc 2 of radius 0.500 meter. Disc 2 in turn drives disc 3, whose radius is 1 meter. The three discs are in contact and there is no slipping. Disc 3 is observed to sweep through one complete revolution every 30 seconds. And we need to solve part A to D of the question. So let us first write down what the question has given us. I have radius of disc 1, which I will write as R1 to be equal to 0.100 meter. Then we have radius of disc 2, R2 as 0.500 meter. Then we have radius of disc 3, R3 as 100 meter. And I have the time period of disc 3. It completes one revolution every 30 seconds. So capital T, which is period of disc 3, is 30 seconds. In part A of the question, they are asking us what is the angular speed of disk 3? So we will call angular speed of disk 3 as omega 3. And we know we can find omega as 2 pi f. I will take f3 for disk 3. Frequency f is related to time period by the expression f equals 1 over t. So here in place of f, I will write 2 pi over t. F as 1 over t. Then we can substitute to calculate omega for disk 3, 2 pi over 30. And when you solve, you get the angular speed of disk 3 as 0.209 radian per second. In part B, the question is asking you, what is the ratio of the tangential velocities of the rims of the three disks? Now, tangential velocity for the three disks will be the same because with whatever tangential velocity or linear velocity disk 1 rotate, the same velocity is imparted to disk 2 and the same velocity is given to disk 3. So if I can find tangential velocity for any one of them, that will be the value for all three. We know the relationship between tangential velocity and angular velocity. Tangential velocity v is given as r times the angular velocity. And since I have angular velocity for disk 3, I can find tangential velocity for disk 3, which will be r3 times omega 3. So let's substitute radius of disk 3 is 1 meter. Omega we calculated as 0.209, which gives me 0.209 meter per second. And this is going to be the same for disk 1 and disk 2. They're all having the same tangential velocity. Now, part C of the question is asking us, what is the angular speed of disk 1 and disk 2? We can find angular speed by relating it to the tangential speed. The relationship between them is v equals r times omega, where v is the tangential speed and omega is the angular speed. So I can find omega by dividing my v with r. We have already calculated the tangential velocity for disk 1 and disk 2 in part B, which is v equals 0.209. We are going to substitute that here to find the angular speed. So we can write omega 1, which is angular speed of disk 1, to be v over r1. And then we substitute 0.209 divided by r1 is 0.1. And when we solve this, we get omega 1 as 2.09 radian per second. And we do the same thing for this 2. Omega 2 will be v over r2, which is 0.209 divided by 0.5. That gives us 0.419 radian per second. So these are the angular speed for disk 1 and disk 2. Part D of the question says, if the motor malfunctions, resulting into an angular acceleration of 0.100 radian per second square for disk 1, what are the disk 2 and disk 3 angular acceleration? So it says when the motor malfunction, angular acceleration of disk 1, which we will call as alpha 1, becomes equal to 0.100 radian per second squared. We need to find what is the angular acceleration for disk 2 and disk 3, which we call as alpha 2 and alpha 3. Now the angular acceleration might change, but the linear acceleration or the tangential acceleration for each of the disks will remain the same. So we are first going to find what is the linear acceleration for all the three disks. And using that, we will find what is alpha 2 and alpha 3. Now the relationship between linear and angular acceleration is Linear acceleration or tangential acceleration at equals r times alpha. So I can find at as r1 times alpha 1. Radius for the first disk is 0.1 times alpha 1, which is 0.1 again. That gives me the tangential acceleration at to be equal to 1 times 10 to the power negative 2 meter per second squared. After I get the tangential acceleration, I can use this to find what is angular acceleration for disk 2 and disk 3. So we are going to use the same expression. We have at as r times alpha, and we will rearrange this term to get alpha equals at over r, a tangential over r. So let's calculate this for disk 2 and disk 3. For disk 2, the angular acceleration alpha 2 will be a tangential over r2, which is 1 times 10 to the power negative 2 divided by r2, which is 0.5. And when you solve this, you get alpha 2 as 2 times 10 to the power negative 2 radian per second squared. And we do the same thing for disk 3. Alpha 3 will be at over r3, which is 1 times 10 to the power negative 2 divided by 1. That gives me the angular acceleration as 1 times 10 to the power negative 2 radian per second squared.